Okay, so today is the second part of optics. So it will be a bit more content today because today we have to complete chapter 2 and we also complete chapter 3. Okay, so for chapter 3 there is revised slides on NTU Learn. So later during the break you may want to download the updated version. Okay, so back to chapter 2. So last week, we started to talk about how to form image. Okay, do you fear there's aircon? No. Okay, okay. If not, I have to call the office again. Okay, so last week we talked about this chapter. We're focusing on how to generate an image. So there are a few things that we have to define first. One is the object distance. The other one is the image distance. Okay, so the object distance is always defined as the distance to the object between the object to the mirror. The image distance is defined as the image from the image to the mirror. And then we learned about there's one golden rule to help us calculate. Oops. Okay. So we have this only one equation in this chapter, which is this 1 over p. Where is it? Okay, this one. 1 over p plus 1 over q equals 1 over f. So regardless of the mirror, it's a flat mirror, it's a concave, or it's a convex. P always stands for the object distance, q always stands for the image distance, and f always stands for the focal length of the mirror. And just keep in mind that the f is half of the radius of curvature, so which means r equals to 2f. So sometimes the question will give you the radius of curvature, which actually is providing you the information of f. Okay, you just have to divide it by 2. Okay, so this is a general equation to calculate where the image is formed by the mirror. But before you do any calculation, don't forget about the summary. I think it's here. Oops, okay, not here. Okay, the summary is on the last part of the slide. Okay, which is this slide. Okay, so last week we concluded with this slide talking about two types of mirror. One is concave. So remember that concave means that the center is more like the spoon. So it means that your light actually, when it comes, it can actually focus light to the center. So it is a real power. It means that this mirror can actually focus a light into the center. That is why the F and R will be positive. Inversely, there is another type of mirror, which is this convex. So convex is actually the opposite side, which is more like the opposite side of the umbrella. So you can always imagine that when the water comes in, it actually will splash everywhere, which means you are never able to find a real focus, a real image. The only thing you can do is you can backtrack into the mirror to find a virtual image. Okay, so this is the biggest difference between the concave and the convex. This one is converging, this one is diverging. And so therefore, this one will give you a negative F and negative R. Other than this, the rest are all the same. For all the mirrors, regardless of the shape, regardless of the F, either it's positive or negative, we always define that in front is positive, behind is negative. Okay, so this is true for all the mirror. Okay, so this is where we left from the last week. Okay, so now moving a bit forward to lens. Okay, so lens is a bit more complicated. So lens, we are dealing with something that is transparent, which basically means that your light actually can penetrate through. So it means the sign will be a bit different. The reason is your light actually can converge to the other side. So it means that you are actually able to form a real image on the other side of the lens. Therefore, the sign is defined a bit different. For lens, it's not always in front is positive, behind is negative. Okay, so it is the same for the P. So for object distance, it's positive in front. Object distance is still negative in front, in the back. However, the Q is different. The only difference is the Q. Because light actually can really propagate through the lens to form a real image, therefore, we define the Q as positive when it's on the other side. Okay, so which means on the same side it will be negative. So this star is very important because this is the only place that is defined different. All the rest you can actually consider it's the definitions are all the same. Again, we have two different types of lens: converging lens or diverging lens. One is F is positive, the other one F is negative. Okay, so mathematically, light can propagate through the mirror, through the lens, and focus on the other side. So according to Snell's law, which we learned in the chapter 1, you should be able to write an equation to express how the light goes through. And then if you take a lot of assumption where the two angle is very small between the incident angle and the refraction angle, and then taking advantage of all these triangle. Okay, so if you're interested, you can try to follow this loop. If not, you can pay attention to the results. Okay, so by taking consideration of light going into a different material, which means you need to take consideration of the refractive index. This is N1, this is N2. And then when you combine everything all together, you get this equation. So then you actually discover that this equation is a bit similar like the image equation. The 1 over P plus 1 over Q equals 1 over F. Okay. However, in this case, because it's a lens, so one thing is a bit different. It's that now your refractive index is different. Before you enter, it's N1, which is air. After you enter, it's actually N2. And then you also have this relationship. So this equation is actually a general equation to solve PQ, image in a lens. Okay, so it's a general equation when a light passes through a lens. You need to use this to solve it. However, in this class, we will take a very big assumption. That is, we consider lens is very thin. What does that mean? Okay, so if you really look at the lens, what happens? So when the light actually penetrates through a lens from N1 to N2, which is likely from air to glass. Okay, so let's say this is a 1.4. So the first thing is you just look at the first interface, which is from air to glass. Okay, so from air to glass, that is the first step. The second step is your light will try to go out. So the second step is if you take the same assumption, which is from glass to air. Okay, so this is a general equation showing that how you should calculate image penetrating through a lens for only one interface. Okay, because it's N1 and N2. But we know that a lens is not only just one interface. A lens actually has two interfaces. The first interface is where your light goes from air to glass. The second interface is when your light trying to come out, which means it's trying to come out from a lens to air. So basically it means that it's a two-step process, coming in and going out. Okay, so if you actually apply this equation 2 times, one to express the light coming into the lens, the other one trying to express the lens escaping the lens, then you will discover that when we apply this equation 2 times, and by putting in the refractive index of air, which is 1, okay, so at the surface 1, this is air to a lens, right? So it's N1 to N2, where your N1 is actually 1, your N2 is actually the refractive index of the lens. And you take all these assumptions by applying this general equation. This is the first equation you'll get, which is N1 is 1, N2 is the refractive index of the lens. Okay, so we stop here. Then, if you move on to the second interface, which is when your light tries to go out from lens, okay, this is a lens, to air. Again, you apply the same equation, but now it's N1 is refractive index of the lens, N2 is 1. Okay, so then this is the general equation again. So now you define this as the second equation. Okay, so now if you combine equation 1 and equation 2, because we know that the process actually should be continuous. One is from, the surface 1 is from air to lens. The surface 2 is from lens to air. So that's why you get a two-step of this equation. So when you put the two equations together, side by side, which we define it as surface 1 and surface 2. And then now if we take another very big assumption, we assume that the lens is so thin that there's no thickness. So which means that when you take assumption that your lens is so thin and there's no thickness, what does it mean? It actually means that your refractive index is not important, right? Because, which means that now if you don't consider the lens is very thick, this thickness doesn't count, which means the refractive index of the lens also doesn't matter that much. Okay, so if you take that, all these assumptions together, which means you assume the lens is so thin like a paper, you can ignore the T, you can ignore the refractive index of the glass. Okay, so in the end, okay, we'll just jump to the solution. So in the end, if you take all those assumptions together, you will discover magically the result is this equation again. Okay, so why this equation has no refractive index anymore? The reason is originally we followed the most strict equation, which is the general equation of lens. And that is when we considered the refractive index of the lens to be calculated. Okay, so that's why we have surface 1, meaning when the light goes into the lens. Surface 2, this equation represents when the light is escaping from the lens. And now we try to assume that your lens is so thin so that the refractive index is not important. The thickness doesn't matter, so you almost have no thickness. So when all these assumptions are taken into consideration, which means that T is 0, thickness, there's no thickness. So your P2 minus Q1 is also 0 because P2 is your second object distance. Q1 is your first image. Okay, so all these, when they apply all together, the result is very surprisingly, you'll discover that this equation goes back to the exact same equation as the mirror. So this is called the thin lens equation. In the mirror, we call it the image equation. Basically, it's the same. So in the end, in this course, you only have to memorize one equation over here, which is this one. Okay, so this equation is called the thin lens equation, which means you can apply this equation to all the thin lens. As long as the question is saying that the lens is symmetric, it is a thin lens, telling you the refractive index of the lens is not important, telling you that the thickness of the lens is, you can ignore it. So in the end, you only need to know what the P is, what the Q is, and what the focal length of the lens is. So it's the exact same equation when you calculate the mirror. Okay, so that's why in this chapter 2, we actually only have one single equation to go through all the questions, including tutorial and your final exam, which is this equation. You are using this equation for mirror. You are also using this equation for lens. So what's the difference? Okay, so the difference is, although they are always defined the same, P is object distance, Q is image distance, F is focal distance, but students usually get wrong. Where? The sign. Okay, so if you ask me what is the most challenging part in this chapter, I would say the sign is the most, I would say the sign is the most challenging part because the sign is defined a bit differently for the Q. Okay? Remember that Q is the image distance. Lens actually can allow light to go through, so you actually get a positive Q after the lens, which means Q is defined negative if it's in front. Okay, so this is the main difference that you need to keep in mind. Okay, so if not, we will try to practice some question by using this equation. Okay, let me think about it. Okay, so we first go to, I think we actually went through it last week before, but we'll do it one more time. Okay, we first go through this example on the next few slides. Okay, so now it's more like a review because last week we actually went through already. So here this is converging lens. And then, okay, I should say it's a thin lens. Okay, so it's a thin converging lens. And then, so which means you can use this equation. Find the location of the image if the object is at 20 cm. Okay, so object at 20 cm means it's P is 20, right? So if you put P as 20, F as 10, because it's provided as 10, then you'll discover that your Q is 20. Okay, so Q is 20. This is very, very important. This tells you that your Q is somewhere over here. Okay, because your Q is positive after the lens. So Q is 20 means that your image should be positioned 20 cm behind of the lens. And then if you calculate your magnification, which is minus Q over P, this is the exact same equation, then you'll discover that it's -1. So it means that it's inverted because it's a negative value, so it's inverted. And then your magnification is 1, okay, because your absolute value is 1. Okay, so the same question, if you change your P, if you change your P distance from P to 8, then you'll discover that your Q is -40. So when Q is -40, now it means what? It means your Q is here, 40 cm. Okay, so this is very important. Q is -40. The negative sign means that your image is not behind the lens. It means that it's in front because it's a negative sign. So it means it's somewhere over here, 40. And again, you still continue to calculate your M. So your M is negative Q over P. Your Q is negative already, so this gives you a positive value. So again, it is a virtual. Why? Because Q is negative. Okay, Q actually determines a lot of information of your image. So because your Q is negative, it means that it's a virtual image. And then your M is positive. It tells that it's upright. And you have an overall magnification of 5 because the absolute value is 5. Okay, last one. When your focal length, when your focal length is still 10, object height is 1, and then now it says that your P is 15. So you put the same equation, but by using P as 15, F as 10, then you'll discover that your Q is about 30. So it means that Q is over here, 30 cm on the right. Okay, so it means your Q is 30, placed on the right-hand side. And then your M value is -2, so it tells you it's inverted. And because your Q is positive 30, it also tells you that it's a real image. Okay, so don't actually think that this is very basic and very simple. I can share with you that even just by such a simple question, asking you to define the real or virtual, inverted or upright correctly, maybe only 50% of students can still get it correctly on the final exam. So given it's a very basic and very standard question, you should and you must be able to write it very accurately. Okay, so why is it real? Because Q is positive. Why is it inverted? Because this follows the sign of the M. Okay, and the magnification is the absolute value of the M. Okay, so this is a practice by using the equation to calculate a lens. Okay, all right. So we also have this another practice where we use this diverging lens as example. Okay, so this is a diverging lens. So what does this mean? It basically tells you that the focal length should be negative. Okay, so here I am kind enough that I actually put a negative sign over here. So if the description actually only says the diverging lens has a focal length of 20, when you do calculation, you still need to put the negative sign. Because this is a diverging lens, it means that light actually cannot focus. The light will only be diverged. So it means that actually it's a negative powered lens. So you have to put a negative sign. Okay, so here we still use the same equation, which is 1 over P plus 1 over Q equals 1 over F. And the F should be negative because it's a diverging lens. Okay, this is where I would say maybe 80 to 90% students calculate wrong. It's due to the sign. They forget to put the F with a negative value. Okay, so then if you remember, and then your P is 30. So in the end, you will calculate a value of Q is 12, but it's negative. Okay, so it's Q is negative 12. Okay, so Q is negative 12. It means that your image should be placed 12 cm somewhere here, right? Because it's a negative sign. Q is negative. It means that your Q is in front of your lens. So it's 12 cm in front of your lens, and which means it's actually on the same side as your object. So that is why it's virtual. Okay, so let's complete. So if you complete the calculation, you complete the M value with the negative Q over P, and then you discover your M is positive 0.4. So here, the final answer is that your image is virtual. Real or virtual depends on the Q. So because you know your Q is negative, okay, your Q is negative, this already tells you it's virtual. Upright or inverted, this depends on your M. Okay, you know your M is positive, so it actually already tells you that it's upright. And a magnification of 0.4, okay, which is the absolute value. Okay, one more. Yeah, I think it's the last one. Okay, so this is, again, the same diverging lens, which means it has no ability to converge light. So it says that this diverging lens has a focal length, 20, but remember, because it's a diverging lens, so you need to put negative 20. Okay, and then it says the object is 50 cm high. Find the location of the image if the P is at the focal point. Okay, so the F is 20 cm, but according to the sign, when you do calculation, you need to put F equals to negative 20. And it says that the P is placed on the focal point, which is here. Okay, so because it's the P is in front of the mirror, so it's P is positive 20 cm. Because P is defined as positive in front. Okay, so P is 20 because it's placed on the focal point. And F is negative 20. So what is the Q? Okay, so then you'll discover that your Q is actually negative 10, which tells you that it's a virtual because Q negative is virtual. So it means that your image is actually somewhere over here, Q, okay? Only here, 10 cm. All right, so P is 20 in front, so it's positive. placed at the focal point over there. F is negative 20, provided by the question. So then you discover that your Q is negative 10. So Q is negative 10, it means that it's in front, okay? So Q is negative, it means it's in front. So it's somewhere over there, okay? 10 cm in front of your lens. And because the Q is negative, so it shows it's a fake image. Okay, so it's virtual. And then upright, because it depends on your M. Your M is positive 0.5. All right, and then finally you have your magnification power, which is 0.5. So the final solution is what is the size of the image. So because your M is 0.5, and originally your object is 50, okay, so 50 times 0.5, which is 25 cm. All right, so basically it's your object height times your magnification power equals to your final image size. Okay, so this is practice of understanding this equation, which is this one, the thin lens equation. So we have actually gone through 5 questions by using the same thin lens equation. Either it's converging lens or it's diverging lens. Okay, so I hope now you should be more or less familiar, but keep in mind that the key is if you remember to put the sign correctly, which is the negative sign. Okay, so other things to mention. Okay, so now one more equation you may find in the slide, which is called the lens maker equation. Okay, so the lens maker equation is actually the original equation for finding the focal length of a lens if the lens is not a thin lens. So as you can see here, this lens is a converging lens. It has two surfaces. This side is defined as R1. This side is defined as R2. So which means that on both sides, it actually has two different radius of curvature. So this is an asymmetric lens because on the two sides, it actually has a different radius of curvature. So the meaning for having this lens maker equation, this is to use when the question is asking you to find the focal length of a lens. Okay, so when the question is asking you to find the focal length of a lens, by providing you that it is not a thin lens, so that is why the refractive index matters. So this refractive index is important because it's not a thin lens. And then because it's not asymmetric, so you have two radius of curvature. One is this R1, the other one is this R2. Okay, so this actually is required when when the question is asking you to find the focal length of a lens which is not a thin lens. Okay, so this one we don't use it to find where the image is basically, because as you can see there's no P, there's no Q. So in the end, close to the final exam, a student will always ask me one question: how do I know when to use this versus how do I know when to use this one? Okay, so it's quite straightforward. This one only applies for thin lens because you can see that the question actually has no refractive index, no radius of curvature. So this is only applied to 90% of the question where it says it's a thin lens. The lens must be very thin. The lens must be symmetric. So therefore you can ignore the thickness, you can ignore the refractive index, you can ignore the radius of curvature of the different sides. What you have to do is just a PQF. And this actually can help you to find the image or find the object. This equation is called lens maker equation. This equation does not help you to find where the image is. Okay, so it's not an equation to find the image. It's not an equation to find where the object is. It's just an equation to calculate the focal length when the lens is not a thin lens. Okay, so like this image, the lens is not thin, the lens is not symmetric, so which means the refractive index does matter. And because it's not symmetric, so you can see that actually there's two different curve or two different surface, which is not symmetric. So there's R1, R2, corresponding to the two different surface. Okay, so this is just an equation when the question asks you to find a particular lens that is not asymmetric, that is not a thin lens, then you use this one. Okay, so try to compare a bit. Okay, so same thing. This is a diverging lens where it actually cannot focus a light. So basically light will be diverged out. So for the same case, you actually can apply the lens maker equation if it provides you this radius of curvature R1 and radius of curvature R2. Okay, it's the same thing. Okay, so we already have gone through these. Okay, so to sum up, I would say the last part of the lens, maybe it's the most valuable part or maybe the most challenging part. So far, I believe you should be more or less very familiar with this thin lens equation, which is 1 over P plus 1 over Q equals 1 over F. Okay, so if you look at the most of the tutorial and the exam question, you actually don't really see a single element. You always see a compound. So, oops, okay. Okay, so we first go to the compound lens first, which is easier. Okay, so if you move to the next slide, you'll see a compound microscope. Okay, so if you pay attention to the past exam paper and tutorial question before, you'll see that most questions appear as a two lens or two mirror, or one lens, one mirror. Why? The reason is a lens, it's alone, standing with one element, usually it has no function. There's no function that you can tune or play around with. So in reality, microscopes, telescope, gyroscopes, many of these optical imaging systems, they are made of two lenses, which means that actually you have the flexibility to design a system. Okay, so what happens to a compound system? How am I going to calculate it? Okay, so before I move on, I want to bring one concept first. So I insert a slide here. Okay, so what is the core value of a compound system? So a compound system basically is like this. You still have, oops. Okay, so let's say it's a compound system of two lenses, which means that you still have this, where is it? Okay, this is your first lens, you have F1. This is your second lens, you have F2. Okay, so the most important value of a compound system is that when your light comes in, your light will focus, right? So let's say your light comes in, your light focus. Okay, so what do you call this? So this we will call it, oops, this is so ugly, okay, never mind. But, okay, so if you just look at the first lens, if this is your object, you will call this as P, right? P1, F1, and this one you will call as Q1. Okay, so if you only look at one system, if you only have one lens, your lens has a focal length of F1, and then whatever your object is placed, this is called P1. So P1 passes through lens, forming an image, or you can say it focus at a point. This is called Q1. Okay, and then here I also have another F. So how can I actually connect this one and this one? There's no way that if I put a two lens, they have to be connected. So the key to connect the two lens or the two system is, okay, so if you look at only this one, right, you still have a P, right? So this is called P2, okay, and then it will focus somewhere called Q2. Okay, so let's say like this. Okay, so the key value to connect two systems is that if you only look at F1, F1 can convert a light at P1 to Q1, right? Okay, and then now ignore this. If you just look at this lens, if I have a focal length number 2, and I have a P, okay, so I call this purple object as my new object. So this is called P2. So P2 passes through F, can also focus at a point, which I define as Q2, right? So if you look at two lenses separately, they actually have their own thin lens equation. All right, so it is 1 over P1 plus 1 over Q1 should equal 1 over F1, right? And over here, it's 1 over P2 plus 1 over Q2 should equal 1 over F2. So when they are separated, they should work and function independently. There's nothing that is supposed to link. Okay, so now if you want to link these two equations together, what does this mean? It means that if you want this to link with this one, now I use a yellow light or maybe an orange light to describe. So if I have a light from here and I want to connect and then focus until here, what does this mean? It means that your position of your Q1 should equal to the position of your P2, right? That is the only way that you can make your light continue to propagate from P1 to F1 to Q1. And then if you want it to continue to go to here, it means that this location, the location of your Q1, which is the location of your image number 1, should and must equal to the same location as your P2. Because it means that only at this location, which is the result of your first image, this image will then subsequently become your new object. So this is your new object distance, and this position will serve as your new P2. Okay, so the key to link the two lenses is that your image from system number 1, which is Q1, this location must also be your new P2. Okay, so which means your new P2. I'm not saying the value of P2 equals to Q1 because this distance can be different. It's just that the location should be the same. So your first image will become your second object. Okay, so your first image, which is your Q1 over here, will therefore become your new object, which is your second object. Okay, so usually what this means is when you calculate this Q1, you'll be able to link it with P2. Okay, so this is how usually the two systems are linked together. So whenever you deal with a compound microscope, compound telescope, it doesn't matter. The first step is you always have to write down two sets of equations. They should work independently. And then keep in mind is that your image from your first lens, which is Q1, should be or should equal or give you the information of P2. Okay, so keep this image in your mind. It's very important. Okay, so this is more or less about what I have drawn just now to show that light has to focus into your first lens onto Q1, and then this will serve as your new object. So it becomes P2 going into F2, and then you get a final image which is called Q2. Okay, so this is how you build a link between the two systems. Okay, so the same thing, you'll see it in telescope. Okay, so here from the slides, this is one real example of some parameter. So you have two lenses, lens 1, lens 2, and then basically you can see that to solve it, you will need two separate systems. One is F1, P1, Q1. The other one is P1, Q1, P2, Q2, F2. Okay, so from two independent systems, you'll get M1, which is your magnification from your first system. For your second system, you'll also get M2. And finally, the total M is the M1 times M2. Okay, so remember that you need to multiply your M1 times your M2. All right, so now we will share some tips for solving this. Okay, so the tips is basically when you deal with a compound system, you need to isolate the two systems. So in this case, this example, it's a converging lens plus a diverging lens, right? So you isolate this as a system 1. And then you can isolate this as system 2. Okay, so what does this mean? It means that actually you should write down two sets of equations first. Okay, so from the first system, it should be 1 over P1 plus 1 over Q1 equals 1 over F1. Okay, so look at this. For your second system, it should be what? It should be 1 over P2 plus 1 over Q2 equals 1 over F2. Okay, so now look at the information you have. Focal length, 5 and negative 8. So you actually have this value. This is 5. This is negative 8. And then it says that a 1 cm object is placed 4 cm from the left lens. Okay, so this is 4 cm. So which means that this value is 4, right? So it's quite straightforward. As you can see here, system 1, system 2, you can first identify that you actually have enough information to solve system 1 already, because P1 is 4, right? P1 is 4. And then F1 is 5. So you actually can solve your Q1, okay? So the first step is actually from your system 1, you already can solve the position of your image, which is Q1. Okay, so basically, by using this thin lens equation, when you apply F is 1, P as 4, you'll discover that you can solve question A. You can solve like your Q is negative 20. Okay, so it means that from the first question, you get an image where? You get an image somewhere over here, Q, 20. All right? Okay, now look at question number B. Is the image produced by the first lens virtual or real? Because it's a negative sign, so it's virtual. Okay, question C. What is the object distance for the second lens? Okay, so now it's time for you to only look at the second system, which is the green one. Okay, so for the green one, we know that F2 is negative 8. And then now you need to search for P2. So what is P2? Okay, so this is very important. So From question A, we already solved that your Q is negative 20, right? So this is Q1. So what does this mean? It actually means that this distance, as I said, the same location, right? So it means that from here to here, this distance is called P2. Okay? So it doesn't matter where your Q1 is. Remember that your Q1, the location of your Q1 always should equal to the location of your P2. So the most important hypothesis is that your image from your first system should be your object in your second system, right? So this becomes your P2. So your P2 is 12 plus 20, okay? So don't forget about this. So remember that, remember what I just draw over here. From your first lens, you get a Q1. Your Q1 is called your first image. Your first image should be your second object, or else the light cannot continue. So it means that the location of your Q1 will also be the location of your P2. Okay? Location of your P1 should be the location of your P2. I'm not saying the value of your Q1 equals the value of your P2. It's the location of your Q1 determines the location of your P2. So in this case, this is Q1. Q1 is over here. So Q1 will now become your new object, which is your P2. Okay? So if this is your new object, it means that from this system, your P2 is actually 12 plus 20, right? Because this is 12, this is 20. So it should be, P2 should be 32 cm. Okay? So P2 is 12 plus 20 because it should be the location where your Q1 is. All right, so P2 is 32. And now you can put 32 back to solve your final image. Okay, so now we know that because your second system, F is negative, and now your P2 is 32, so you get a Q of negative 6.4. All right, so this is virtual. And then finally, you can calculate your M1, M2, and the total M is M1 times M2. All right, so this is an example of a compound system by making it more complicated, because now you have one is a converging lens, the other one is a diverging lens. Okay, so the last part is some application. So we know that it is very important that lens can actually correct our eye as accommodation. So it can be divided into a nearsighted and farsighted. So we know that nearsighted means that you actually need, okay, so if you look at this image, what is the definition of nearsighted and farsighted? So a nearsighted basically means that the image doesn't form on your retina. Oops, sorry. Okay, so what you need is actually you need a diverging lens to help it to extend to your retina. Farsighted means that your image is actually more further away from your retina. So actually you need a converging lens to help you converge back onto your retina. So there is only one thing to remember, that is called diopter. So diopter is usually the parameter where you go to take a prescription of a lens, and then where it helps you to measure the power. So the power is defined as 1 over f. It means that you need to know what is the power, what is the focal length of your lens. So let's say that your focal length is positive 20, then your diopter is P equals to 1 divided by 20. If your lens is negative focal length, then your diopter is also negative. Okay, so actually when you go to some store to buy a swimming goggle or you buy a normal lens, you always will see this value, positive or negative. So if you're nearsighted, you should always look for -1 because you actually need nearsighted eyeglass, which is a diverging lens that is f negative. If you are farsighted, you should always to look for a diopter P that is positive, because you need a lens that is a positive value to help you correct your eye lens. Okay, so here is one example. So if somebody can see very clearly, and you know that your diopter is -4, what is the focal length of your eyeglass? Okay, so basically it's 1 divided by P to solve it. Okay, so this is very straightforward. But in reality, people actually don't really use the focal length. They actually convert this into diopter, the capital P, to represent the lens, the power of the lens that you need. All right, so here is one application, calculating the lens. And the other application is this compound. So as said, compound is very complicated in terms of calculation. But if you think of it, you actually just need to break it down into a two system. Because originally they are independent, and now you're trying to connect the two systems together. So the link is that you need to remember that your Q1 should equal the location of your P2. Okay, then you can actually solve this. Okay, so in your tutorials, you will see a lot of questions on this. It can be mirror plus mirror. It can be mirror plus lens. All right, so in summary, I would say for this chapter 2, okay, so chapter 2 basically more or less is about this diagram. As you can see, we have been talking about how to calculate the image. So there's two types of lens, two types of mirror. All four actually utilizes the same equation, which is 1 over P plus 1 over Q equals 1 over F. For mirror, remember that this slide actually summarizes everything. Oops, okay. Okay, so for mirror, it is very important that you remember this slide. Definition for everything in front is positive. Everything in the back is negative. And remember that for converging, diverging, the key is you need to put a negative sign. Okay, so this is for mirror. For lens, it is much more complicated. Why? Because your light actually can go through, which means your Q is defined as positive after the lens, but negative in front. Otherwise, P is the same. Okay, so still we share the same equation. Luckily, you can still use this. Thin lens equation. Oops. Okay, you can still use this thin lens equation to help you calculate all the questions. So all the questions rely on this thin lens equation, which means you should either know your P, your Q, or your F. And again, pay attention to the sign. The sign is usually where you will get it wrong. And lastly, the most difficult part is when you deal with a compound. So a compound is actually nothing too different. It's just that now you need to deal with two sets of image equation. So the first step you should do is you need to write down two independent sets. And you consider you solve this one first or you solve that one first. It really depends on what parameter you have. Okay, so for tomorrow's tutorial, we will demonstrate a lot of solutions on calculating between a compound system. But the key is, remember, the first image should serve as your second object. Okay, this is the very important concept for a compound system. All right, so if not, we will end this topic over here, and then we will take a short break. And then after the break, we will move on to chapter 3. Okay, so we will take a 5+ minutes break. If you have any questions, you can come to the front. Okay, so now moving on to chapter 3. Okay, so chapter 3 is on wave optics. So as we said, the first two chapters is dealing with when light is considered as a straight line, which is we call as a ray. From chapter 3 and chapter 4, we now consider light as a wave, which means light actually has the property like an ocean wave. So that is why it's defined as wave optics. Okay, so I would, honestly speaking, I think most students find this topic the most difficult. So I will try to break it down into some concept that you can understand it better. Okay, so talking about wave optics, to begin with, it means that now we don't consider light only as a straight line, which means what? Which means that this is something that actually you see very commonly in daily life, like the bubble, the rainbow color, or you can see these oil on the ground with these rainbow color feature as well. So the difference between chapter 1 and 2 is it's called ray optics, which means that light can be blocked. So wherever it's blocked, you don't see a light, where we call a shadow. Now in chapter 3 and 4, we consider light as a wave, which means light has the property of like an ocean wave. So it means it can bend, it can go up and down. So you can imagine that now light has the property to squeeze into a hole and come out. So after squeezing a lot of light into a tiny hole, the new light coming out can actually expand to become very big. And then you can imagine, because they were squeezed into the hole and then they come out all together, so many of the light can interact with each other, where in the past, light doesn't interact. There's no interaction. The light is blocked, then it's blocked. The light is passed through, is passed through. In wave optics, because light is now much more complicated, it has a lot of property. It has the property of a frequency, amplitude, wavelength, as much as you can imagine from a wave function. So imagine that all these properties, when you accumulate all together, the light actually can interact with each other. So that is why there's a lot of phenomena that is generated that you can see in daily life, which actually cannot be explained. Because in rays, light doesn't really interact with each other. More or less, they can form an image. But when light is a wave, you get a lot of new property. Okay, so when we deal with a wave, this is what we often think of, which is a sinusoidal wave. So now you might have this concept in your mind. We know that you can really straightforward define light as a sinusoidal wave, which means it has an amplitude, and your light travels through time. So which means that you actually can define a certain frequency depending on how much wave you have per second. You also can define one thing called wavelength. So we know that the wavelength is defined as the distance between one wave to one wave. So this is called the wavelength. Okay, so all of these should not be very unfamiliar. It's when you deal with wave function, when you deal with a sinusoidal wave, these are some properties that you often see. So today, what I want to introduce, and it's the most important part for this topic, is another property that maybe in the past we don't really talk about, which is called phase. And it's also why most students get very confused. So phase is a new property. Now we want to add on top of this sinusoidal wave. So what does a phase actually mean in terms of light? So as you can see in this small video, oops, okay. So the phase, by definition, you can see it says it's a fraction. The fraction of a wave cycle compared to its origin. Okay, so it's the only thing you may catch is fraction. Okay, so now I use one example to help you understand. Okay, so basically, the idea of phase is like this. So this is a running track. So you run, we know that if this is the NTU's track field, so if one route, let's say you know one route is 1 km, okay? So if a person says he starts to run until here, so if a person tells you that he already actually run 1/4, this is a fraction, then you actually know that he actually ran 250 meters. So this is called phase. You know that the person is running on a cycle. So one cycle is 1 km. So if I tell you you're on a cycle of 1/4, then you actually know the distance, because you know that one cycle is 1 km and 1/4 is 250 meters. Okay, so this is a concept of a phase. If I actually tell you I or you or a person can run this one cycle, let's say in 4 minutes. Okay, so 4 minutes you can complete one cycle. So if I tell you actually I ran half cycle, which is I tell you I ran 1/2, you actually know I already spent 2 minutes already. Okay, so this is the basic concept of a phase. A phase can tell you two information. One is time, the other one is distance. So the basic concept is, let's assume that one cycle, you think of a track. So one cycle corresponds to a certain distance, which is 1 kilometer. And you know that according to your velocity, to complete one cycle, you actually need 4 minutes. So if I already know this information, then as long as you tell me your phase, if your phase is 1/4, then I can know what is the distance you have already run. If I know what is your phase, I can also tell the distance. I can also tell the time that you have already spent. Okay, so a phase is the concept of fraction in one cycle, which actually gives you the information of the distance, how much the light has been traveled by distance. It also tells you the information in time, the time domain, how many time the light actually already has been traveling. Okay, so now you imagine that now I convert everything very officially. So one cycle is how much? One cycle is 2 pi, which is also equivalent to 330 degrees. Okay, so which means if I tell you your phase change is pi/2, pi/2 is actually 90 degrees, which is corresponding to 1/4. If I tell you your phase change is pi, that is half of 2 pi, right? So which is 180. Okay, so to become more official, one cycle in mathematics is equivalent to 2 pi, or 360 degrees. So we usually express in how many pi, that fraction, either it's a 1/2 pi, 1/4 pi, the how many pi actually can tell you the fraction in one cycle to tell people how much distance you have been already traveled and how many minutes you have been already running. Okay, so if you have this image in your mind, now you can come back to look at this slide. So one cycle is usually defined as 360 degrees, which is also equivalent to 2 pi. Okay, so basically, phase means the fraction that you have been traveling in this cycle. So the phase is important because it actually can tell people two information. As said, one is the distance, which is the space domain. As long as I know the phase, I actually know how much you have been traveling. The second is the time domain. So as long as I know how much phase you have, I can actually predict how much time you have been already spending in this cycle. Okay, so this phase is a new property that I want to introduce you when we talk about light. Why? Because we know that now we treat light as a wave. So when light is traveling, it is important that you catch the information of how much distance the light has been traveling and how much time has the light been traveled. Okay, so that is why we need to understand the phase. Okay, so usually when all the phase is connected, we call it a wavefront. So that is representing like when you imagine a bunch of army, and then when they propagate in one direction, when you connect all the armies together, they form the forefront of the light. That is called a wavefront. Okay, so for instance, if this is light shining from the center to outside, so this is the direction that the light is trying to spread out. And then what happens is that actually you can express that the light is actually traveled in a wave-like. So these are all called wavefronts. Okay, so wavefront must be perpendicular to the traveling direction of your light. Okay, the wavefront must be perpendicular to your traveling distance. So for instance, in this case, your light is traveling from here to here, and this red curve is defined as the wavefront. Okay, so these are some basic concepts of the property of light when you consider light as a wave. Okay, so it's perpendicular to your wavefront. Okay, so again, because if you define light as a wave, so there's a lot of property that you can calculate, which is number one is the speed. So if you know the speed, you can calculate the distance. And because of this, you must heard of wavelength. Okay, so the wavelength is originated when you consider light as a wave function. So which means that your light actually has a so-called wavelength property. So the wavelength is defined by v equals to lambda times f. Okay, so this is velocity. Lambda is your wavelength. F is the frequency. So remember that your wavelength is always the inverse of your frequency. So this goes back to when we talk about this refractive index. If you remember this chart, every material has a different refractive index. And this refractive index also is dependent on different wavelength of light. So if you remember in last week's tutorial, we also mentioned about a lot about this wavelength. So the wavelength is resulted from when we consider light as a wave. Okay, so this is just a reminder. Okay, so now we are moving to the most important topic of today. How can you actually write the definition of a phase? So let's assume the origin is 0, so this term is gone. So the basic property of a phase can be written as 2 pi times L over lambda. Okay, how do you visualize this? So phase is defined by one cycle is 2 pi. This cycle, let's say, you have been traveling a distance of L, and you know that one cycle should be 2 lambda, right? So your fraction, which is L over lambda, because lambda is the distance that when you travel one cycle. So one cycle equivalent to 1 lambda. L is the distance from your P to the source, which means it's actually the actual distance that you have been traveling. So L over lambda is a fraction. Your fraction times the 2 pi. This term is defined as the phase. Okay, so if you want to calculate what is the phase, this is how you should write it. 2 pi L over lambda. And depending on the source, So let's say originally the source is 0. So then the first term is gone. If the first source is already non-zero, let's say your source already contains 1 pi, then actually you can add 1 pi on top of it. Okay, so this is the phase, the definition. Okay, so when your light travels, you should expect that nothing is going to be very smooth. So there's going to be something happening that is called a phase change or phase shift. So which means that when originally your light is traveling nicely, and now your light will bump into a wall. So what happens is there's two scenarios, N1, N2. Okay, so if your light travels and bump into a material that is a higher refractive index, which means that it forms an obstacle to change your phase. So what happens is that your reflected wave will now have a certain amount of shift compared to your original light. So which means in this case, if N1 is smaller than N2, your reflected wave will experience a phase change of pi. Oppositely, if N1 is bigger than N2, you imagine that this is something like you are stepping into from water to air. So basically, it's nothing is being an obstacle. So your phase change will become 0 because nothing will cause your phase to change. Okay, this part is a rule you need to remember. Okay, so before this slide, what we are trying to showcase is that a light is a wave. When you consider light as a wave, there are several properties. There's frequency, there's amplitude, and there's also a property called phase. Okay, so phase is the key property that we are going to deal with in this course. So phase, by definition, is a fraction amount showing how much your photon has been traveling in one cycle. This can tell you the distance of your light that has been traveling. It also tells the time, how much time your light has also been traveling. Okay, so therefore, if you define the physical definition of a phase is that one cycle corresponds to 2 pi. It is also equivalent to the distance of lambda. So the actual distance that you have been traveling is L. So L divided by lambda times 2 pi is the definition of a phase. Okay, so this is something must be new to you. So try to understand this concept. Okay, and then phase, since it's established, so now you imagine that light actually, when it travels, it can bump into different material. So if the material is larger in terms of refractive index, you imagine that you encounter something which is like an obstacle. So your phase will become changed. So your phase will shift a little bit in terms of a pi. However, if your phase hits N1, N2, but N2 is actually smaller, you imagine that nothing is causing your phase to change. So therefore, it's 0. Okay, so this is a rule of thumb that you need to remember by yourself. When a light is traveling, encountering a second interface, a second material, you need to consider the refractive index. Either the refractive index, if it's larger, it means that you are hitting into a wall. So you imagine when you hit into a wall, and then when you walk backward, maybe your property will change, right? Because it's something that is actually quite solid. So you will experience a pi in terms of your phase shift for your reflection wave. However, if you are traveling into a material that is very soft, and even softer than your original material, so you actually feel nothing at all. So you imagine that you are actually walking from water to air. In this case, you are unchanged, okay? So your reflection wave doesn't change at all, so your phase shift is 0. Okay, so in this case, you need to determine either your N1 is bigger than N2 or your N2 is bigger than N1 to help you identify when your light wave is traveling, when it meets a different material, what happens to your phase shift. All right, so that is topic 1. So just a very quick summary. So in topic 1, what I want to introduce you is that instead of considering light as a ray, now we deal light as a wave. So which means that all the properties that you have learned in the past for a wave should appear. You can use the same concept to visualize a light, which means your light actually can now travel in a wave. Okay? And then besides this, we want to introduce you something new today, which is called a phase. So by definition, phase means fraction. It tells you a certain fraction amount of your light that is traveling in one cycle. So we know that one cycle is equivalent to 2 pi, or 360 degrees. So if you actually know the phase, it actually tells you information of the light. By how? So let's say now if this is you, and then we know that one cycle is 2 pi, which is 360 degrees. So if I actually know your phase is 1/4 or 1/2, I actually can tell the distance or the time you have been running on the track. Okay, so in summary, phase can provide you the information of a space domain. It can also tell you the information of the time. Just by thinking of this diagram, I hope you can understand the phase better. So we have this definition of phase, 2 pi. L is the actual distance that you are running in one cycle. So one cycle is correspond to one wavelength, which is equivalent to here to here. Okay, so this is one wavelength. All right. Okay, so lastly, phase is an intrinsic property of light. So you need to understand that the phase does change when it encounters a different interface. So if your light encounters an interface that is very solid, that is even bigger and harder than your original interface, which means if N2 is bigger than N1, then you imagine that your reflection wave will have a phase shift of pi. If your light is traveling from into a refractive index that is smaller, then what happens is you actually don't feel it. So your reflection wave actually is maintained. Nothing is changed. So your phase shift is 0. All right? So in the first 20 minutes, what I want to convey you is the property of light as a wave. And then I hope you understand that what is a phase, although it's not very easy to understand. Okay, so now moving on to the most important topic of chapter 3, which is called interference. So when you talk about interference, you might think of people and people interfering with each other. So here is actually the same concept. When you have two lights, each light has its own phase. So now it comes back to why we need to understand phase. Because when you actually have two rays doesn't have that much to talk about. But when these two rays are waves, there's a lot of things you need to consider. So now you assume that when in reality you have two waves, which is like two light sources, when they meet each other, they interact. So which means in the end, you are dealing with the interference between not two people, but two light waves. Okay, so the key is the two lights interact with each other, and they cause interference. So interference can be a plus or it can be a minus. So let's say that if originally your number 1 and number 2, they have the same phase. So same phase basically means that their wavelength, their amplitude, everything is aligned. So what you get is that your resulting wave is like 2 times, double. If your number 1 and number 2 light, their phase is totally opposite, it means that whenever they travel, they cancel out each other. So this is what we call a destructive interference. So in the end, you'll discover that they cancel out each other. So your interference becomes 0, like a destructive one. Okay, so now the basic concept is that when you have 2 lights, each light has its own phase. So the 2 phases can interact with each other. So this is what we call interference. So how does it really happen? So in this course, we are going to introduce, in reality, there's actually 2 commonly seen methods that actually makes interference to happen. Okay, so the first one is that you imagine that when your light passes through 2 tiny holes, and then ray 1, ray 2, they will meet on the screen. So if you're clever enough, you will discover that actually there is a certain amount of difference between ray 1 and ray 2. This is called delta R. Okay, so you can imagine because there is a certain amount of distance between ray 1 and ray 2, this will definitely cause a phase difference between the 2 waves. Okay, so here the definition. When a light passes through a tiny structure, OPL is created. Okay, remember OPL is the optical path length. So this ray 1, ray 2, there's a difference between the 2 rays, so which is delta R. This delta R is the origin of interference because this delta R is defined as the optical path length difference, and this optical path length difference will create this phase difference. Okay, so that is why you'll see interference. Another method is that when your light comes down, let's say coming down from the top, and then it meets a thin film, so you get your first reflection at the first interface, and then you get a second reflection at the second interface. Okay, so what happens is that number 1, number 2, they also experience a 2D amount of change. So you imagine that originally you have 1 light coming down, and then now your light meets the first interface, you get a number 1 reflection, and then your light, the other light goes down, and this thin film is thickness is D. So actually, the difference between ray 1 and ray 2 is 2D, right? Because this is D, coming down 1 time is 1D, going backward is 2D. So ray 1 minus ray 2 is 2D. Here, this is also ray 1 minus ray 2 is delta R. This one is 2D. Okay, so again, you are creating a certain amount of optical path length difference. So this amount of optical path length difference will create a phase difference. Okay, so remember the origin of interference is that when your light can be split into 2 lights, and somehow they have a certain amount of optical path length difference created, then you imagine that these 2 lights, when they interact with each other, they will have interference. Okay, so this is the cause of interference. You must have two lights. The two lights must have a certain amount of optical path length difference to be generated in order to see this phase change. Okay, so mathematically, again, remember that we can use this phase difference to express light. So now if I try to use a mathematical way to write it, so now if I have two light source 1, light source 2, and remember the phase is defined by 2 pi, L1 over lambda, L2 over lambda. So if now these two subtract, right? So which means that if now my two light, the two phase subtract each other, then what happens is that it becomes 2 pi L1 over lambda minus 2 pi L2 over lambda. So in the end, I can write it as 2 pi delta L over lambda. So this is a very general form of phase difference. And then depending on how much change in terms of my lambda is, so if this is equivalent to integral of pi, then it's a constructive. If this is equivalent to half of the wavelength, then it's destructive. Okay, so this is how mathematically we write the phase difference. Okay, so in the end, we can, again, we have two types of phase difference. One is constructive, the other one is destructive. Okay, so constructive means that you will get a double effect, which is a brighter fringe. If it's destructive, it means that it will become darker. So what you get is 0, which is cancel out each other. Okay, so in the second part of this chapter 3, on top of what we have learned about phase, so now you understand that every light has phase. Each light has its own phase. So when there's two lights and then they travel in space, if they have the chance to meet each other, then they will contribute so-called interference. So the most common way to generate interference is that your light actually meets a structure that actually will split your light. So the first one is that when the light comes in, but your light actually meets a lot of tiny holes. So these tiny holes will split your light into two. So you create a certain amount of optical path length changes. The second method is that when your light comes down, shining on a very, very thin film, it's thin enough that it creates a separation between your first ray and second ray. So you imagine that your first ray and second ray, it also created a difference in terms of 2D. And this also creates an optical path length difference that is sufficient enough to create a phase change. Okay, so mathematically you can write the phase change in this way. All right, so now we move on, but before we move on, I'll play this short video. Oops, let me see. Yeah. It's not working.
We'll work on the example of a soap bubble, but before that, when you pay close attention, you can see some pretty cool stuff and turns out all of thin film up with the bubble there might be a color missing over here. I think reflected from the bottom surface.
Okay, so this video, okay, please pay attention. So this video is actually part of a final exam. So this video actually shows why a soap bubble actually can create rainbow pattern. So as you can see here, this is a soap bubble. So a soap bubble actually is a structure of air, soap, air. Okay, air, soap, air. So actually the layer is so thin that you may not even notice. But actually if you enlarge this part, it's actually something like this. It can be air, water, air, or air, soap, air. So this is the thin layer that creates the interference. Okay, so what happens is when a broad band of light comes in, so your light should consist of a rainbow color. Okay, so your light consists of a lot of color, and then when your light comes in, because this very thin layer, it will actually separate your light into two different reflection. One is directly reflecting from the top surface. The other one will be reflecting from the bottom surface. So as you can imagine, that the top and the bottom actually has undergo a different optical path length. So if you consider the difference, this number 2 versus number 1 has a difference in terms of a 2t or 2nt. You need to consider the refractive index, so it's a 2nt. Okay, so oops. All right. So this, when you visualize from your eyes, what you see is actually the interference between ray 1 and ray 2. So it is important that you understand the difference between ray number 1 and ray number 2. Okay, so visualizing this, I'll go back to our slides. Okay, so if you still remember, we just mentioned about that when your light encounters a different material, you need to ask yourself if your light refractive index is bigger to a bigger or to a smaller material. If it's encountering a bigger one, it will change in terms of pi. If it's encountering a smaller refractive index, which means it's a no phase change. Okay, so now if you apply this thing to what we just saw. Okay, so here we have one example. This is air, SiO2, and silicon. And then if I tell you that when one light shines down, it will generate two reflection. One is number 1. The other one is number 2. Okay, so number 1 is air to silicon dioxide. Okay, so air to silicon dioxide is from a smaller to bigger refractive index. So you actually generate, so in this transition from N1 to N2, you actually create a phase change of pi. And then at this second interface, when you transit from SiO2 to silicon, you also transit, you get a smaller to bigger refractive index. So you also get phase change of pi. So your phase change is actually pi minus pi. So when you compare ray 1 versus ray 2, your phase change is actually 0. Okay? So if your phase change between ray 1 and ray 2 is 0, then you need to use this set of equation to calculate your bright fringe and dark fringe. Okay, so it means that, remember that your optical pattern difference is 2nt. Because between ray 1 and ray 2, the difference that it has been traveling is 2nt. So your optical path length difference is 2T. If you want to generate a bright fringe, it should equal to m lambda. If you want to generate a dark fringe, it should equal to m plus 1 over 2 lambda, which is a half lambda. Okay, so this is the golden rule that you need to memorize and understand for all the questions you will meet in this chapter. Okay, so one more time. Basically, the first step is when you meet this type of question, you need to figure out that where your interference is coming from. So it is always the middle layer, the thin layer that is creating this interference. So in this case, it is actually this layer. So which means that you need to focus on this layer. So when your light passes through this layer, it creates two reflections. One is on the top. The other one is on the bottom. So it basically creates ray 1 and ray 2. And if you actually compare what is the difference between ray 1 and ray 2, the difference is 2T. In terms of how much they have been traveling. So why is it 2? Because when you come down, it's 1. When you go back, it's 2. So the difference between ray 1 and ray 2 is 2T. So the difference is delta L is 2T. If your difference of 2T is equivalent to a full set of lambda, then you get the bright fringe. If it's half set of lambda, then you get a dark fringe. Another case is opposite. In this case, it's an air, film, air. This is where the thin film is. All right, so you get two reflections. One is here. The other one is here, number 1 and number 2. So please ask yourself, at the first interface, which is air to film, it's from a small to big. So you generate pi. For the second interface, it's from film to air, which is bigger to smaller. So you generate a phase change of 0. So pi minus 0 is pi. Okay, so this is the other set. If your phase change is pi, then it means that because initially you already have a pi difference, so if you want to generate a bright fringe, you just need to add a half lambda, right? So again, bright fringe, in this case, your delta L equals to 2Nt equals to m plus 1 over 2 lambda. If you want to generate a dark fringe, because initially you already have a pi, so it's 2Nt equals to m lambda. Okay, so these two slides are very important. You need to keep in mind, totally understand. Basically, it looks like there's 4 sets of equation, but you don't need to memorize all. You just need to memorize one set. If the phase change is 0, bright fringe is m lambda, dark fringe is m plus 1 over 2 lambda. The other set is just a swap. Okay, so you only have to remember if phase change is 0, then it's bright fringe m lambda, dark is m plus 1 over 2. The other one is the swap between dark and bright. So if phase change is pi, the only thing you need to do is actually just remember to swap between the dark and the bright. Okay, so again, in daily life, we actually see this very common. You can see this pattern, which we call Newton ring. This is a result of interference. And then in your tutorial, you also will see this question. Why? Okay, so when you have two glass, and your two glass actually is separated by a thin layer, this is the layer that creates the interference. So eventually what you see is dark, bright fringes. So this is what we are trying to calculate. So from the top view, we will see a lot of these stripe. These stripe represents this interference. This one also is the same case as this. Okay, this is bubble. Okay, so the tips to solve this type of question is basically the first step is that you need to identify where is the thin film. And then find ray 1 and ray 2. So then you will define out what is the phase for ray 1, what is the phase for ray 2, and you need to ask yourself the difference between N1 and N2. Then you calculate the phase difference. So then you know that what equation you need to apply. Either it's this set or it's the other set. Okay, so here I show you one example. So here I say this is a structure with air, film, air again. Please find the thickness of this film. Okay, so if I say that the order is 1, we just need to focus on the first order. So the first step is you need to identify where is the thin film. Okay, so here is the yellow part, and this is your first reflection. This is your second reflection. So for your first reflection, it's air to film, so your phase change is pi. Your second reflection is film to air, so it's 0. So delta is pi, so which tells you should use this set of equation. Okay, so now if you want to find the thickness of the film at m lambda, if you are looking for destructive, then you use this set. If you're looking for constructive, then you use the n plus 1 over 2. So if you're looking for destructive or constructive, here is the solution. And then the T is the thickness. Okay, so you put in the order of light, which is m equal to 1. So 2nt equals m lambda, 2nt equals m lambda. Okay, m plus 1 over 2 lambda. Okay, I just want to remind you just one time. This 2nt, the nt is tied to each other. If your t is this part, your n also should be this part. Okay, so on the final exam, many students, they know how to write 2nt equals to m lambda. But they usually put the n value, either it's the air or I don't know why, somewhere else. But please remember, 2nt, the n should always correspond to the refractive index of the t, right? So else it doesn't mean the optical path length. Nt is the definition of optical path length. So your refractive index should be tied where your t is. If you accidentally put the refractive index of air or somewhere else, you will get 0, okay? So there's no partial point if you write the nt wrong. The nt, I already reminded several times. N is tied with the t. The t is the thickness of the thin film. The n is the refractive index of the t. Okay, so here, t is the thin film, so this is the refractive index of the thin film. Okay, question number 2. Again, find the thickness for the first order if the light is operating at 500 nanometer. So here again, you have air, film, oleo. So this is surface 1. This is surface 2. So at surface A, your phase change is from air to film, which is from small to big. At surface B is from film to oleo, which is also small to big. So it's pi and pi. So the difference is 0. So 0 means that for bright fringe, 2nt equals m lambda. For dark fringe, m plus 1 over lambda equals 2nt. Okay, so it's the other set. So again, for dark fringe, for bright fringe, you just need to put in the correct number to solve the thickness. Okay, so again, remember, here, okay, I think this is wrong. Okay, so for instance, this is a wrong solution. If you want to find the bright fringe, right, it should be 2nt equal to m lambda for bright fringe. And remember that in this case, this is the thin film, right? So this is the T. So the T should be 1.5. Okay, so this is this should be 1.5. Okay, so this is not correct. Okay, so this n should be 1.5 since this is the refractive index. The refractive index should be linked with the refractive index of the thickness where you're dealing with. So this is correct. Okay, so this 1 should be 1.5, not 1.0. Okay, so this is just an example that many students will put the wrong number. But please remember the T is the should be tied where the refractive index is of the thin film. Okay, so here the solution is as this. Okay, so the last example is this one. Okay, so this one, student may be very confused. So on the surface of CD or your camera, you might see these rainbow color coating. So what exactly is here? So it is actually a bunch of these periodic structure that looks something like this. So basically you have a pitch structure like this. Okay, so what is the phase change? Okay, so phase change must be dealing with optical path length. Okay, so you can think about it, what is the optical path length over here? Okay, so this is a solution. So if you look at this structure, this is the top layer, and this is the bottom layer. When your light comes down, it can meet the top layer and go back. Okay, so you assume the first light 1, is L plus L. Okay, assuming that the distance on the top is L and going back is L. Your second set of light wave will actually meet the bottom, which is L plus T and L plus T, right? Because it's L plus T, and then the reflected wave is also L plus T. So in the end, the difference between wave 1 and wave 2 is 2T or 2NT, to be accurate. Okay, so even though this question, it looks a bit different from the multi-layer part, the multi-layer question, you still have to understand that interference must result between two waves. So you need to find where is the two reflection. So you can see in this diagram, the difference in terms of the structure, it actually created two different reflections. One is a reflection from the top. The other one is a reflection from the pit, which is the ground level, bottom level. So if you compare ray 1 and ray 2, the difference between ray 1 and ray 2 is actually 2T or 2NT. So it's actually, again, the same equation. So if you want to calculate your interference, you should also utilize the 2NT equals to m lambda, or 2NT equals to m plus 1 over 2 lambda. All right, so think about it. We'll have a short break over here before we move on to the next part. Next week, the whole topic. Yes.
Topic 1 to 3, right? Until this one as well.
1 to 4.
1 to 4.
But 4 is quite related to this one. So it will be very, very less on 4. Okay, so now moving on to the moving on to the last part for today. Okay, so students are asking about the next week quiz. So next week quiz is from topic 1 to topic 4. But because topic 4, the last part is very similar to this part, so it will actually be less focused on topic 4. Okay, so which means you can just mainly focus on topic 1 and to topic 3, which is we'll be covering now. Okay, so the last part of interference is when the light passes through a tiny hole, it actually can split the light. Okay, which means that rather than previous focusing the light on a thin film, a more common way to generate interference is that when your light actually passes through a tiny hole. So it is very straightforward that when your light passes through a tiny hole, it will split your light into two paths, which is ray 1 and ray 2. Okay, so previously we mentioned that when your light is split into ray 1 and ray 2, there is a certain amount of optical path length difference between ray 1 and ray 2. And according to the triangle calculation, this difference can be written as d sine theta. Okay, so basically, this theta is the theta between this top triangle over here. Okay, so delta L equals to d sine theta. This delta L is actually the difference between R1 and R2. And then if you further write d sine theta, we know that if you want to generate a bright fringe, it means that your optical path length difference should equal to full integral. So it should equal to m lambda. And because we always assume that your theta is very small, so sine theta equals to tangent theta, and tangent theta equals to y over L. So in the end, you get this equation, y equals to L m lambda over d. Okay, so this y is the fringe. So what does this mean? In reality, your light actually can generate a lot of things like this. This is the result that you see over here on the screen. Okay, so what happens here is you will see a lot of bright and dark fringe. So this y actually represents what? It represents, let's say this is your first fringe, it represents the distance that you can see the fringe from the center. All right, so in reality, on the screen, you will see a series of fringes. So y is defined as the distance from the center, which is the origin, to the fringe. So if you are trying to find the first bright fringe, which is L times m lambda over d, the d is the distance of this slit. M is the order of the light. Lambda is the wavelength of the light. L is the distance to the screen. So this is the first order. If you're looking for the second order, then you put m as 2. Then that is the second order. If you put m as 3, then that will be your third order. So in summary, if you want to find the fringe on the screen, you can assume that you will see two types. One is bright, the other one is dark. So again, we have constructive, we also have destructive. So constructive means that your delta L, which is your optical path length difference, should equal to m lambda, which is a full integral difference of lambda. If you want to see dark fringe, which is destructive, it means that your delta L, the difference between ray 1 and ray 2, should equal to a half set of lambda, which is m plus 1 over 2 lambda. Okay, so this relationship will yield these two equations correspondingly to find the location of the fringe. Okay, so many students in the end will be very confused about what is the definition of of y. So y is the distance that you can find the fringe on the screen compared to the center. Okay, so as said, okay, so let's say that this is the result you see on the screen. So I would say this is called y1, for instance. This is called y2. Okay, so y2 means the second order of the light compared to the center. So let's say this is 0. So this is called y1. This is called y2. Okay, this is called y1. And then this distance is called y2. Okay, so y means the distance that you can find the fringes to the screen, or to the center. Okay, so oppositely, if you're looking at dark, so if this is a dark, so this will be the first dark, this distance will be the second dark, this will be your third dark. Okay, so it basically means that you can either find the location of bright fringe. You may also be interested in finding the location of the dark fringe. So if you have this picture in mind, now you can go back to look at these two equations again. So white bright meaning the location where you can find the fringe of the bright fringe. So M is the order, first, second, third. Dark is where you can see the dark part of the fringe, and M is the order that is corresponding to the light, like this. Okay, so tomorrow we will also have some tutorial questions related to this. Okay, so, oops, okay. So in summary, in the interference part, there's actually two types. The first type is by using a thin film, which is these bottom two. It basically means that you are using a thin layer to create multi-reflection. So these two is referring to, you have a thin layer, you create reflection number 1, reflection number 2, and the difference between this is called 2 and t, okay, because this distance is called t. Okay, so please have this image in your mind. The first type of way, the first method to generate interference is that when your light comes down, it encounters a thin film that can split your light into two reflections. So between ray 1 and ray 2, you have a difference in terms of 2 and t, because going down is 1t, going back is 2t. And please remember to remember the refractive index of this material. So this is a very short image to help you understand what is 2 and t. So for this type, your optical path length is always 2 and t. But for bright fringe and dark fringe, is a bit different. If your phase change is 0, then 2 and t equals m lambda for bright, and m plus 1 over 2 for dark. If your phase change is pi initially, then 2 and t equals to m plus 1 over 2 for bright, 2 and t equals to m lambda for dark. Okay, so this is one set. Okay, for the other set, which is this one, the double slit. Okay, so double slit basically means that when your light encounters double hole, or double slit, it will split your light into two. So again, you can see that interference is always talking about using a structure or a material that can split your light into two. So now after your light passes through the double slit, it will separate into ray 1 and ray 2. So the difference between ray 1 and ray 2 is d sine theta, according to calculation. All right, so this is where this is coming from, this part. The optical path length difference is d sine theta. And if it's bright fringe, is equal to m lambda. If it's dark fringe, it equals to m plus 1 over 2 lambda. On top of this, you have one set of equation to remember, but you actually do not have to remember the equation because actually the equation is provided on your formula sheet during your final exam as well as your quiz. It's just it's more important that you know which set to use. Okay, so for dark and bright, the Y is to calculate the location of the fringe. Okay, location of the fringe. Either it's for bright or either it's for dark. M is the order of the light. Okay, it can be 0 to infinite. All right, so this is the two-set of equation that is linked with the double slit. Okay, all right, so the last topic is about some application. So here we introduce one thing called resolution. Okay, so resolution, it might be more or less familiar. It means that if you have the ability to see something very clearly. So of course, this one is well resolved. This one is very bad because you actually cannot resolve it very well. Okay, so what does this have to do with interference? Okay, let me see this part. Okay, so resolution basically means that you have two lights, or you have one light anyway, but it will be split into two. And when you see on the screen, if you can see the two lights very well. Okay, so this is a bit similar like when we talk about light passing through the two slits. Okay, so now you imagine that you have lights coming out from a structure, and then they reach on the screen. So here, the second topic is that we want to understand if actually you are able to see the two lights very well on the screen. They can overlap, or they can actually be split very clearly. So this is the definition of resolution. Okay, so there is a very simple equation to talk about resolution. Is that when light passes through a single slit, okay, well, a single slit is defined something like this, instead of just a double slit. Okay, so when a light passes through a single slit, and then reach to a screen, okay, or reach to some two objects. So if you want to resolve S1 and S2, it means that you need to open up a certain angle, okay? So this angle between your camera or between your element, it doesn't matter. So you imagine that the first step is there is an angle. It also can be your eyes, okay? So it can be your camera lens, it can be your eyes. So in terms of resolution, it means that if you want to see something S1 and S2 clearly, which means you need to be able to separate S1 and S2. What is the minimum angle that is required for you to distinguish between S1 and S2? Okay, so this is the definition of the angular resolution. Okay, the angle that you need to open up in order that you can see the two objects or two lights very clearly. But in reality, we know that our eyes are circular, lens are circular, microscope are circular. So there is one equation to resolve it. So it's the 1.22 lambda over d. So most cases, I would say 90% of the question, when it says you're dealing with a human eye, you're dealing with a lens, dealing with a microscope, dealing with a circular aperture, as long as it's a circular element, this 1.22 is required because it's a constant to fix the linear one. So the previous one is, you can understand it as if you consider everything on a 2D version, a 2D plane, what is the angle you need to open so you can see two objects clearly. But in reality, we have this 1.22 to fix this single slit issue, which is because in most cases we need a circular aperture. All right, so this equation is more common, 1.22 lambda over d. So now d becomes the definition of the diameter of the aperture. So you can still visualize it as something like this. you need to open your eyes to see S1 and S2. It's just that this part you imagine is kind of like a lens or a human eye. So this D actually represents the diameter of the aperture rather than the length of a slit. Okay? So now if you want to know how far apart you actually can distinguish between S1 and S2, here is one example. So now you can see that assuming the reading distance is 25 cm, the diameter of a human pupil is 4 millimeter, and operating at 550 nanometer. What is the human eye resolution in pixel? Okay, so what is this question asking? This question is asking what is the resolution in terms of pixel. So it means that you should be finding the distance between S1 and S2. So if you still recall that when you deal with an image, you deal with a camera, you deal with a monitor, you always ask about what is the pixel size. Is the pixel size good enough to resolve an image? Is the pixel size good enough to resolve a particular object on a camera? This pixel, actually you're asking about the distance between S1 and S2. Okay, so to solve this, the first step is, number one, you need to find out what is the minimum angle. You need to open up your aperture. Okay, so again, the first thing is you need to solve this angular resolution. So the angular resolution is defined as 1.22 lambda over d. So lambda is 550. D is the diameter of your pupil, so it's 4 millimeter. So this gives you the result in radians. So this is the theta that is required for you to open up your eyes or your lens in order to visualize S1 and S2. Okay, now the second step, which is quite important. In reality, if I'm asking you what is the pixel separation, which means that what is the distance between S1 and S2, then you need to find out by using D equals theta times L. Okay, where theta means the angle, L is the distance. Okay, we take the assumption of because the L is very far away and theta is very small, so we actually take advantage of when theta is very small, it's equivalent to sine theta, which is also equivalent to tangent theta. Okay, so that is why in the end, we can use the pixel separation D as this minimum angle times the L. Okay, so that will give you what is your pixel number. Okay, so this is the commonly used equation to find the minimum angle for resolution. So if you look at this equation, if you are lucky enough, you will see on the quiz in many questions. So what are some methods that you can increase the resolution? So that refers to looking at this equation. If you want to increase the resolution, which means that you want to, what? Okay, which means that you want to make this as small as possible, right? So increasing resolution doesn't mean you want the angle to be as big as possible. Increased resolution means that you want to have a better resolution, which means that the smaller the angle, the better, which means you can resolve under a very, very small angle. So in order to get a smaller minimum angle, one method you can do is to shorten your wavelength. Another method you can do is to increase your size of the aperture, right? Okay, so think about it. To increase resolution means that you can resolve something under a smaller scale, which means you can use a smaller angle to resolve something. That means you need to make this value smaller, right? So either you can shorten your wavelength or increase your diameter of your aperture. Okay, similarly, we know that the pixel separation is d equals to theta times L, right? So d equals to theta times L. So again, if question asks you, how can you increase the pixel separation, then of course you can try to increase this value, which means increase the wavelength, right? Because if you increase the wavelength, which means the theta will be bigger, then the pixel separation will be larger. Or decrease the size of aperture, right? So which means you want to make the d smaller. All right, so think about it. A higher resolution means that it should come in a smaller angle, okay, and a smaller d, okay. A bad resolution means that you need to you need to resolve with a bigger angle and a bigger d. Okay, so it's the concept is quite inversely, because good resolution doesn't mean the value is high. It means that the value should be small. Okay, a bad resolution actually refers to a value like theta is very big. All right, so this is about resolution. So very quick summary. So today, the chapter 3 is, I would say, one of the most challenging topic for most students. So the first topic is talking about wave optics, which is when we now, on top of light, we want to introduce light as a wave. So here the parameter that we introduce is called phase. So phase, I hope you understand that it's a topic talking about fraction. How much distance and how much time your light has been traveling in one cycle. Okay, so it's corresponding to 2 pi. So physically, mathematically, it should be written as 2 pi times L over lambda, where lambda is called wavelength. All right, so this is phase. So in terms of phase, every light has its own phase. The phase will not change until it bounces a wall. Okay, so the phase will only change when it meets a second material. So if the material has a larger refractive index, then your phase will change and result in the pi. So the phase shift is pi. If it encounters a material with a lower refractive index, so it's more like you assume there's nothing blocking, so it's a 0. Okay, so this is the rule of thumb that you need to use when you try to manage dealing with phase change. So here, moving on to the real topic of today, which is interference. So interference basically means that you at least have to have 2 lights, right? 2 lights, which is 2 waves. The 2 waves will interfere with each other, and that is why we are calling it interference. So what is exactly interfering? It is the phase. So that is why in topic 1, you need to understand what is the phase. Okay, so why phase can be changed? So basically, it's when a light meets a structure that has multiple holes, it can split the light into multiple rays so that it actually creates a difference in terms of their optical path length. And this can change the phase. Okay, so the phase change, therefore, you create interference. Another method is that when your light meets a very thin layer, that it actually will split your light ray into 2. One from the top reflection, the other from the bottom surface reflection. And when you compare the ray 1 and ray 2 again, you also will discover that there is a certain amount of optical path length difference named as 2D, or 2ND. The N should correspond to the refractive index of this material. So in both cases, you generate a certain amount of optical path length, and that is the origin of phase change. So from the first type, basically, is when light encounters a thin film. So you generate ray 1 and ray 2. So logically, the first thing is you need to ask yourself, where is the thin layer that is creating the 2 rays of reflection? And then you have to ask yourself, what is the phase change between the 2 reflections? so that you can determine what set of equation to use. Okay, either it's 0 or either it's pi. And remember, the 2nt equals to m lambda. The nt, again and again, I want to remind you, the n is the refractive index of the t. Okay, so then this is the tip to solve it. Okay, and then the second method to generate interference is by using a slit, where when the light passes through a slit, it generates multiple rays. So in short, if you have two rays, you create a certain delta R. And mathematically, this delta R is equivalent to d sine theta. From here, we get an equation that can help you to calculate the location of the fringe. So what is a fringe? The fringe is actually the pattern of the interference. So for instance, on the screen, you may see something like this. So the value of y basically means the distance from the center to the first fringe, the center to the first dark fringe, the center to the first or the second dark fringe, or the bright fringe. Okay? So if you have this, if this is bright and this is the center, so this is called y1, this is called y2. All right? So I hope you understand the definition of the fringes. So in summary, you have this table to help you summarize the two types of interference that we are talking about in this course. The last topic today is on resolution, which basically is meaning that when the light passes through a small aperture and then creating, let's say, two images on the wall, how am I able to resolve it? So we actually come up with this final resolution equation, which is this 1.22 lambda over d. So remember, this 1.22 is only used for circular aperture, which is like a lens, microscope, or human eyes. So it's actually a two-step process. First, you need to find what is the minimum angle that is required to see the two objects. The second process is you need to find the d. Okay, so the d is defined as the distance that you can see between S1 and S2. All right, so then this will help you to find the resolution. Okay, then please spend few more minutes at home to think about this slide, how to increase resolution, and what parameters does contribute to resolution, what parameters does not contribute to resolution. Okay, so basically for the quiz, I would say topic 4 is not much about it, because topic 4 is actually an extension of this double slit. So more or less, it's topic 3 already covered the content of topic 4. So if you don't have much time, I would suggest that you basically just focus on topic 1, 2, and 3. All right? So these 3 topics until now, it will actually cover everything that you need on your quiz. So there will be a sample quiz uploaded on NTU Learn, and then there will be a lockdown browser. So please try to see if your laptop can work well with the lockdown browser. So it will be next Friday. So next Friday will be the quiz 1. And if you really have any issues that you cannot attend quiz 1, you just need to let me know in advance with a proper reason and evidence, so that then you can attend the makeup quiz, which will be held on a later date. Okay, so if you have any questions, you can let me know later before the quiz. If not, this will be end of the chapter 3. All right, thank you.